Okay. Well, all right. So this is a little note just put together for well, just people, I guess, about symmetry. So this is kind of something that you just think of if you're into math. So this is what okay. Right, this. Here we have that. Simple case, and I'll kind of generalize it after that. But this one, this doesn't have problem. So certainly you can see the symmetry in it, symmetric about the y-axis. But there's also another symmetry, I guess, the one that kind of comes up if you think about these things. And so this is how it kind of goes. If you have, what you're looking at are two normal lines at symmetric points on the parabola. Okay, so you have one here, let's say, a symmetric point on this side. Okay, so, and we'll look at the x coordinate, each one of those. So this is, let's call it x0, negative x0 over here. Okay, so if you know a little bit of calculus, I guess that's pretty much the starting point here. So you get a tangent line there and a tangent line over here. Okay. So you have your slopes, which are given by the derivative. And you also have what are the normal lines actually are perpendicular to these two. They actually intersect, is what I'm going to show, is that they actually end up intersecting in a single point, actually on this line, x equals 0. And that's always the case, right? So you start the setup, this function, and you have these symmetric points. So you have x0, really you're just specifying this number, and then you get your symmetric point on the other side there. Okay. So let's write down the equations of these two. So for the normal line here, this point, first let's be right here. 2 points. So this point is x0, 0. That's the coordinate there. Same thing over here. Negative x0. So the slope of the tangent line is the derivative f prime at x0. So we know the slope of that line. The slope of the normal line is just going to have the negative reciprocal of that. Okay. So the equation of the normal line here, going to be the difference. So using the point slope form would be the way to go with that, I guess. So y minus the y coordinate of the point. Okay, so the y coordinate of the point that this line passes through is right here. It's equal to the slope. Okay, so the slope is the negative reciprocal of the tangent line. The slope of the tangent line is f prime of x0. So this is negative 1 over f prime of x0. Y minus the y coordinate is the slope x minus the x coordinate of the. Okay, so that's the point slope form applied to this normal line. There. All right, and you do the same thing, you can get the same kind of equation for this normal line over here, but with negative x0 in place of x. Okay, so it looks very similar. You get y minus x0 equals y negative x0. Then you have x plus x0 because it would be minus negative. Okay, so you got this line and this line. They both intersect at this point, which you can see once you simplify everything else. Okay, so that's the starting point. And then to write these down, you get the derivative here. We get 2x. Okay, so let's write these, simplify this here. So y minus f of x0, that's x0 squared, negative 1 over f prime at x0, it's 2x0. And then this is x minus the form there. Same thing over here, do a similar kind of simplification. Y minus negative x0, they plug that in there, you get x0 squared, the negative when you square it becomes a positive. Y minus x0 squared looks the same as what we have over there. And this is minus 1 over the derivative of that negative x0. So it's negative 2x0. Okay. The derivative evaluated negative x0 and negative 2x0. Okay, there. Then we've got still x plus x0 left. So then we can just simplify that. Equals 2x0. Okay, so these are our two equations. Remember, x0 is a fixed number, so this is really just a function of x. Okay, so these are both of these lines. And with the equations of both of these lines, we can then show that these two lines actually intersect along this axis. So with these two, this line here or this line over here, you can see that the point of intersection is the point xy that makes both of these equations true. So you just have to solve this system. Okay. So to solve that, you can see that the left side is the same in each one. So you can really just equate the right sides in each one. Okay. So you know that for both of these, you know that 1 over 2x0 x plus x0 equals this here, 1 over 2x0. So you can see what's going to happen now. The 2x0s cancel, and you multiply through by that. Okay, again, I didn't specify it, but assuming that x0 is actually positive or non-zero, so it's going to be somewhere up here. Okay, of course, we don't want to be divided by 0, so that kind of gets rid of that. And then multiply through, and what are you left with? Because x plus 0 is equal to, remember the minus out here, you get negative x plus x0. What happens? The x0s cancel, so you get x is negative x, or 2x 0. In other words, x must be 0. So the x coordinate of the point where they intersect must be on this axis. So that's what that proves. But we can actually say a little bit more. We can say what the y coordinate of that point is too. And all you have to do is substitute that value into either one of these equations we came up with for the normal line. Okay. So to get the y coordinate, we just have to plug this back in. I'll plug it into the first one here. So you get y minus 0 squared equals negative 1 over 2x0 times 0 minus x0. The coordinates is 0, comma, the y coordinate given by that equation. Okay, can you guys even see that? Yeah, maybe not. Y coordinate 0 squared equals, we simplify this, we just get 1 half. So sum of y squared. So that gives you the y coordinate. So you can see the picture. If you slide this x0, you make x0 go to 0, this whole thing comes down here. Okay, it can't actually equal 0, but you can take a limit. You can actually take a limit here. And what happens, so my intuition when I first thought of this would be, oh, well, these would go up to infinity. The intersection point would go up to infinity because you got these coming in. Seems like it's getting more and more vertical as you get to the origin here. But in fact, it ends up going to 1/2, which you can see from this formula. Okay, so that's actually the smallest value that never actually achieves, but that would be its limiting value. Okay. And then it's going to range from 1/2 up to infinity. So up to infinity, that would be all the intersection points that you can get in this way. Okay. So what you can say is that as x0 goes to 0 from the right, okay, because again we started with x0 some positive value, and then the symmetric point over here. So x0 is positive, so x0 can approach 0 from the right. It makes sense. We can do that, but we can't make it 0 because remember in this whole discussion, it's going to be something that's positive. Okay, and the slope of the normal line is also going to go to infinity as you approach. But as you get closer and closer, this is going to actually go to 1/2. So you actually have a minimum. It never actually achieves it, but that's its limiting value. Okay. So there's a similar kind of treatment that you can give for a function rather than just x squared. You could also look at just x to the 2n. And in this case, if you do the same kind of setup, it's still going to intersect at the y-axis, but that minimum value is not going to be a 1/2, but it's actually going to be a function of n. Okay, so you can kind of look into that, or if you want to do that, I can go through that too. But anyways, that's a little bit about symmetry. So you can see how that all comes into play here. Okay, we leave that now. This will work. Let's see.